Hello, this will be a demonstration of Proposition 31 from Book 3 of Euclid's Elements, which states that in a circle, the angle in a semicircle is a right angle, the angle in a major segment is less than a right angle, and the angle in a minor segment is greater than a right angle, and furthermore, that the angle of a major segment is greater than a right angle, and the angle of a minor segment is less than a right angle. We are given the circle ABCD. We have some diameter of it, BC. And we have the center of it, E, which is, we'll say, is about there. And we have these straight lines, BA, CA, and then DA and DC. So here's something that looks like this. And we have set out to prove that this angle BAC, which is in a semicircle, is a right angle. So this angle BAC is a right angle. That this angle ABC, which is in the major segment ABC, this angle here ABC is less than a right angle. And this angle ADC in the minor segment ADC is greater than a right angle. And furthermore, that this angle of the major segment BAC, so that would be the horned angle BAC, like that, is greater than a right angle. And furthermore, that the angle of the minor segment here, this angle DAC, is less than a right angle. We begin by drawing the straight line EA. This is obviously by postulate 1. And then by postulate 2, we produce the straight line BA, some arbitrary length f. Okay. Now we know that BA, not BA, BE and EA must be equal because they're radii of the same circle. That's definition 115. And so in this triangle BAE, we have two equal sides, and so the angles which these equal sides subtend, it must be equal. That is to say that the angle EAB is equal to the angle ABE. This is Proposition 1.5. And similarly, we know that EA is equal to EC, and so the angles which these straight lines obtend must be equal. And that is to say that the angle EAC is equal to the angle ACE. So again, that's Proposition 1.5. And so if we add these equals together, common notion 2 tells us that the sums will be equal. So that we can say that the whole angle BAC, which is BAE plus EAC, this whole angle BAC, is equal to ABE plus ACE. This is, again, just simple common notion 2, adding equals to equals. Now we also know that this exterior angle here, FAC, right, it's an exterior angle to the whole triangle ABC, is equal to the two interior and opposite angles. That's Proposition 132. So that is to say that the angle FAC is equal to ABC plus ACB. Now we also know that the angle BAC is equal to ABC plus ACB. And so that means, by common notion 1, that the angles BAC and FAC are equal to each other. And we know that when adjacent angles are equal, each angle is a right angle. And so we can say that this angle here, BAC, must be a right angle, like so. Now, when we look at this triangle ABC, we know that if we add any two angles together, their sum must be less than two right angles. That's Proposition 117. And so we know that the angle BAC plus ABC must be less than two right angles. And because one of these angles in this sum simply is a right angle, the only way that we can add these two angles together such that they are less than two right angles is if this remaining angle ABC is less than a right angle itself. This is a property of magnitudes. So we can say that the angle ABC is less than a right angle. Now, if we look at this whole cyclic quadrilateral we got going on here, the quadrilateral ABCD, if we add the opposite angles of a cyclic quadrilateral together, we know that we'll get two right angles. And so when we take the opposite angles ABC and ADC, we know that these two angles, ABC plus ADC, must equal two right angles. That's Proposition 322. And if one of them is less than a right angle, the only way that the two of them taken together can equal two right angles is if the remaining angle is greater than a right angle, and that is to tell us that the angle ADC, which remains, must be greater than a right angle. Now finally, we can see it that this angle BAC, or this horned angle BAC, contains the right angle BAC. And so we know that the horned angle BAC must be greater than the right angle BAC. And that is to say that the horned angle BAC is simply greater than a right angle. Similarly, we can see it that the horned angle DAC is a part of the right angle FAC, which means that the horned angle DAC is less than the whole angle FAC. This is all common notion 5, parts being less than wholes and wholes being greater than parts. And so if the angle FAC is a right angle, which we have proven, and the horned angle DAC is a part of it, then the horned angle DAC must be less than a right angle. Now this all being what we set out to prove, we are done with the proposition, therefore, etc., QED. You might hear the first part of this proposition that the angle in a semicircle is a right angle. You might hear it called Thales' theorem. That's a common name for it in the same way that 147 is Pythagoras' theorem. 331, or at least part of it, can be considered Thales' theorem. That is all I have to say about this proposition, so I will move on simply to 332.